Okay, so I'm going to work a couple problems here, and I'm going to start off with an admittance problem. So most of these problems that I'm going to work are going to have to do with complex impedances or admittances, complex power, that sort of thing. Okay, so this is the problem, and you see I've gone ahead and put the answer there, but I think a number of people are having trouble with how to get the answer. So if I were you, I would not watch my video. I would see if you can come up with this answer, and if you can, then you're in good shape. If not, then watch the video and try to find out where your mistake is, and then once you find out where the mistake is, see if you can complete, from there and so forth, so you can learn how to get to the end of the problem. One of the things that I think is often happening in these types of problems is people are just having problems using their calculator to enter the complex numbers and get the right answers through that. And so it's pretty important to understand how to use your calculator properly, especially going back and forth between rectangular form for complex numbers and polar form. So basically real and imaginary parts to magnitude and phase. That's a pretty important concept and something that can easily mess you up here. Okay, so in this problem it says two admittances y1 and y2 are in parallel. Okay, so let's just draw that. Okay, here we have y1 and we have it is in parallel with y2. And a third admittance y3 is in series with that parallel combination. Okay, so we'll put y3 in series here. Okay, it says if a current I1, 0.1 angle 30, is flowing through y1, find the magnitude of the voltage across the entire network. Okay, so I'll assume that they're having this 0.1 angle 30 going down here. Obviously they probably should tell you which way it is flowing through there, because that would reference the voltage in one way or the next. I'm going to assume it's flowing down, and so that's what we're going to work with. It says find the magnitude of the voltage across the entire network, so it's really wanting to know what is, if we call this voltage here V, the phasor is the magnitude of V, e to the j angle of V, and it wants to know just the magnitude. So how am I going to get the magnitude? Well, this isn't as hard as it seems. One thing we do know is that current, and it's trying to make us use admittances. I think most of the time people are familiar with impedances, and so let's just sort of go through this problem based off of the impedance approach, at least at first. So most of the time we think, okay, V equals IZ. Well, Z is just 1 over Y, so this is I over Y. So this is our formula for the voltage, general voltage for a current through an admittance. So we know that we have 0.1 angle 30 through y1, so we can find, I'll call this voltage here V1, and V1 is equal to then 0.1 angle 30 degrees. And that could also say that's 0.1 e to the j 30 degrees, either way, divided by y1, which is, what do they give it to us as? 3 plus j4 millisiemens. So that's times 10 to the minus third Siemens. I won't even write the Siemens because my top units was in, it doesn't say that, but I'll presume they're saying that I1, 0.1 angle 30, is in amps. So it could be in milliamps, in which case that would be I need to add something, but I'm pretty confident that this is just in amps. Okay, so I've got amps, and I went ahead and put the 10 to the minus third for the Siemens, so this will come out in volts. And so if I run this through my calculator, let's see what I get. Okay, when I calculate that, I get 18.39 minus J 7.86, which of course I could convert to polar form and get 20 angle minus 23.13 degrees. Okay, so that gives me V1. Now look, once I know V1, I have these two nodes are the nodes for Y1, and notice that's the same two nodes for Y2. That, you know, these two are connected by a bare wire, these two are connected by a bare wire, so it's the same node on the top and the same node on the bottom, so the voltage is the same. So that gives me the voltage across Y2. Okay, well, that's helpful to me, but what I really need is I need this current through Y2. So I'll call this current I2, and so I know that I have V1, and it's also equal to I2 over Y2. And so if I have that, then I can say this is equal to, or this is going to give me I2, which is V1 Y2. So my V1 I've got is 20 angle minus 23.13 degrees, and my Y2 is 5 plus J2, and now that's millisiemens, so I'm going to say times 10 to the minus 3. Maybe I'll 5 plus J2, both of those, times 10 to the minus 3. So that'll have me in Siemens. And so I've got those two multiplied by each other. So the voltage times the admittance, this will give me that current. And let's see what I get out of that here. So I get 0.1077 with an angle of minus 1.33 degrees. Okay, that's all the significant digits I'm going to put there. Okay, so coming back over here, I've got that, and I'll also write this just to make sure in real and imaginary parts you can see it. I'll convert it back to rectangular form, and so that's equal to 0.10767 minus J 2.5 times 10 to the minus 3, and that's just that one is times 10 to the minus 3. The other one is 0.10767 just by itself. Okay, so maybe to make sure that's clear, I'll put it that way. Alright, so now I have I2, and I need the current here so that I can get the voltage across that impedance Y3, which I'll just go ahead and call V3. Okay, well I know that current because I've got I1 and I2, and I can, if I want to call this I3, I can write an equation at that node that says minus I3 plus I1 plus I2 is equal to 0. So that gives me that I3 is equal to I1 plus I2. So when I calculate I1 plus I2, then I get my numbers are right, 0.194 plus J 4.75 times 10 to the minus 6, which in polar form is 0.2 angle 13.74 degrees. Okay, so that's I3, and now I need to give V3, or get V3, and V3 is equal to I3 over Y3, and so, okay, I've got I3, so that's the 0.2 angle 13.74 degrees, and Y3 they give me up here at the top is 2 minus J4 millisiemens, and so 10 to the minus 3. So when I do this, I'll get for V3 in rectangular form 9.93 plus J 43.6. Now I've got all my units, so that would be in volts, but let me go ahead and convert this to magnitude and phase as well. So in magnitude and phase, that would be 44.72 angle 77.2 degrees. Okay, so now I have V3. Now if I want to find that voltage that I called V there, well, notice I can write an equation around the loop that says minus V plus V3 plus V1 equals 0. So V is equal to V3 plus V1. So that's what I got to calculate. And I got to calculate this 44.72 angle 77.2 degrees plus what was V1? V1 was 20 angle minus 23.13 degrees. Now I could do that in add the two answers in polar form, but actually it's easier to add those things in rectangular form. So I'll say that that's 18.39. My V1, I'm going to take this rectangular form for it. So this is V1 here. And then V3, I'll take the rectangular form of that there. So V is equal to that plus that. So you can see that I've got right here 44.7 angle 77.2. That is my V3. So just to make sure it's clear, I'm going to convert that back to rectangular. So that's 9.93 plus J 43.6, and then I'm going to add to that 18.39 minus J 7.86. So I add those two together, and I get 28. So V is equal to 28.31, or 32, plus J 35.75. And that's the real plus J imaginary part, and in polar form, this is equal to 45.6 angle 51.6 degrees. Okay, so they wanted to know here for this problem, they wanted to know what is the magnitude of V, and it's 45.6 degrees. So magnitude of V is 45.6 degrees. And notice, what's the answer? 45.6 volts. For such, I said degrees, excuse me. I don't know where I got that from. Volts. One other thing I should point out here, notice you might think that you could take, can I take the magnitude of V is equal to the magnitude of V1 plus the magnitude of V3? We'll look at that. The magnitude of V1, where did I have that somewhere. Magnitude of V1 is 20. We calculated that right there. The magnitude of V3 is 44.72. So, well, obviously you can see we're trying to ask that question, is 45.6 the same as 20 plus, forgot that number already, 44.72? Obviously not. So it doesn't work to take the magnitude of one plus the magnitude of the other to get the magnitude of the total. And why not? Well, remember, the phase has to be incorporated, and so when we incorporate the phase into the voltages, you know, you have the magnitude times the cosine of the phase plus the magnitude times the sine of the phase times J. When we do that and add those up, you can see it will cancel out some of the voltage, or maybe it could add up to such that the magnitude of the total thing does not have to equal the magnitude of the two added up together. Now, obviously, it could, and that would happen in the case of DC, or when everything is in phase. So the magnitude could possibly end up being the total magnitude could be the two added together, but that's a special case when everything is in phase, and you know, in general should expect that that's not going to be the case for these complex circuits, or when I mean complex, these circuits with complex numbers in it, because you don't necessarily expect all of the voltages to have the same phase angle like that. Okay, so that's this first problem.